In this EzEd video lecture, we will learn different concepts of AC circuits, such as AC signal, generation of the AC signal, different terminologies of AC signal like form factor, peak factor, phase angle, phasor of the signal, in-phase and out-of-phase signals, Phasor algebra, and the fundamental AC circuits such as purely resistive, purely inductive, and purely capacitive circuit. There are two types of signals, DC signal and AC signal. The magnitude of the DC signal always remains constant, irrespective of time. But the magnitude of the AC signal keeps on changing continuously with respect to time. Hence, these signals are abbreviated as direct current for DC and alternating current for AC. Let's focus on the AC signal only. This form of signals finds many applications throughout the world. Its magnitude can be stepped up or stepped down very easily using transformers. AC signal generators provide more power and efficiency in the generation of the AC signal than the DC generators. Due to these advantages, AC signal is used for the transmission of electricity throughout the world. And that is why we get AC signal at our homes, which we refer to as AC mains. Thus, the AC signal continuously changes its magnitude above and below zero levels. For every alternate period from 0 to pi, 2 pi to 3 pi and so on, we get the positive magnitude for the signal. This half is hence called as positive half. Similarly, for the duration from pi to 2 pi, 3 pi to 4 pi and so on, the AC signal gives the negative magnitude. This half is thus termed as the negative half of the AC signal. There are different forms of the alternating signal such as sinusoidal wave, triangular wave, square wave, sawtooth wave, etc., out of which we will only consider the sinusoidal wave for the further studies.
Seriously, pay attention. This is important.
Let's study some commonly used terminologies in AC signals. The first term is the instantaneous value. The value of the alternating quantity at a particular instant of time is called as the instantaneous value. In the signal shown, V1 and V2 are the instantaneous values of sine wave at time t1 and t2 respectively. The second term is the cycle. One complete set of positive and negative values of an alternating quantity is called as a cycle. The third term is the time period. The time taken by the alternating signal to complete one cycle is called as the time period. It is denoted by capital T and is measured in seconds. Thus, capital T represents the time period and small t represents the time instant. The fourth term related to the AC signal is the frequency. Number of cycles completed per second by the alternating signal is called as frequency, denoted by F and measured in hertz. The frequency is reciprocal of the time period, thus F is equal to 1 upon T. The last term to study is the amplitude. The maximum value attained by the alternating signal in the positive as well as the negative half is called as the amplitude of the signal. It is represented by Vm. So let's see how this AC signal is generated. The AC generator consists of a permanent magnet with opposite poles, two wires that act as a conductor and an armature that joins the two conductors. The two ends of the conductors are connected to the external circuit. As soon as the armature starts rotating in either clockwise or counterclockwise direction, it cuts the magnitude field lines generated by the permanent magnet. This induces an EMF in the coil and the current starts to flow as shown. Thus, the generator gives a continuous output with the alternative positive and the negative magnitude signal, which we refer to as the AC signal or the sinusoidal signal. This signal is mathematically represented as V equals Vm sine omega t. As omega and Vm are independent of time, the signal depends on the sine function. Thus, we call it as a sinusoidal signal. In this equation, small v is the instantaneous value, Vm is the maximum value of the signal, omega is the angular frequency, and t is the time instant. The same equation can also be written for the instantaneous current also. Let's take an example now. An AC current is given by I equals 150 sine 30 pi into t. Find the maximum value, the frequency, the time period, and the instantaneous value at t equals 5 seconds. So we need to find maximum value of the AC current, the frequency, the time period, and the instantaneous value of the current. The given equation is I equals 150 sine 30 pi into t. Comparing this equation with the standard equation, we get the maximum value of the current is equal to 150 amperes. The frequency is calculated from the angular velocity. We know that omega equals 2 pi into f. Thus we get the frequency f equal to 15 Hz. The time period is the reciprocal of the frequency. Thus t is equal to 66.66 milliseconds. To calculate the instantaneous value of the signal at t equals 5 seconds, we substitute all the values in the standard equation I equals Im sin omega t. Hence at t equals 5 seconds, we get I equals 140.03 amperes.
Seriously, pay attention. This is important.
In case of the AC signal, the magnitude of the signal is expressed in three different ways as the peak value, the average value, and the root mean square value. Let's see the peak value first. It is the maximum value attained by the signal. The signal attains maximum value when omega t equals 90 degrees or sin omega t equals 1. It is represented by Vm or Im. The second way to express the magnitude of the AC signal is the average value. The arithmetical average of all the values of an alternating quantity over one cycle is called as its average value. It is calculated as the area under the curve upon the base length. Now there are two main categories of the signals, such as the symmetrical signal and the asymmetrical signal. The signal is symmetrical if its positive cycle is exactly equal to the negative cycle. And if the positive cycle differs from the negative cycle, the signal is asymmetrical. Few examples of symmetrical and asymmetrical signals are as shown. For the symmetrical signals, the average value calculated over one complete cycle becomes 0 as both the halves are the same. Thus we calculate the average over a half cycle only as the average value equal to the area of half cycle upon the base length of the half cycle. For the asymmetrical signals, the average is calculated as the ratio of the area of the full cycle to the base length of the full cycle. Let's take an example. Find the average value of the asymmetrical signal shown. From the diagram, the signal can be represented as V equals 10 sine theta for the interval of theta between 0 to pi and V equals 0 for the interval pi to 2 pi. Thus the average value is calculated as the average voltage equals area of full cycle upon the base length of full cycle. The area is calculated by integrating the signal over one complete cycle. Thus we get average voltage equal to 1 upon 2 pi integration 0 to pi Vd theta plus integration pi to 2 pi Vd theta. On solving this definite integration, we get the answer as average voltage is equal to 3.183 volts.
Hey, it's time to concentrate now.
The magnitude of the AC signal is also represented as the root mean square or RMS value. Let's assume that the DC current flows through the circuit for the time t producing X amount of heat. Now let's assume that the AC current flows through the circuit for the same time t producing the random amount of heat. If the amount of heat produced by both the current is same, then the values of the AC current and the DC current are equal. Thus when we compare the AC current with the DC current, we always consider the root mean square value of the AC current. For the symmetrical waveforms, the RMS value is calculated as the root of the ratio of the square of the area of the half cycle to the base length of the half cycle. Whereas for the asymmetrical waveforms, it is given by the root of the ratio of the square of the area of the full cycle to the base length of the full cycle. Let's illustrate the concept of RMS value by considering the following example. Find the RMS value of the signal shown below. As the given wave is symmetrical, we calculate the RMS value for half cycle only. Thus, Vrms equal to the square root of the ratio of the integration of v squared dt upon 4. On solving the integration, we get the value of RMS voltage as Vrms equal to square root of 133.33 equal to 11.54 volts. The relationship between the average value, the RMS value, and the peak value is determined by the two quantities, the form factor and the peak factor. The ratio of the RMS value to the average value of the AC signal is called as the form factor. The form factor always comes out to be around 1.11. The ratio of the maximum value to the RMS value is called as the peak factor. For the alternating quantity, the peak factor comes out to be approximately equal to 1.414. Consider an example on these concepts. If the equation of the AC current is I equals 100 sin 300t, find the frequency, the maximum value, the RMS value, the average value, the form factor, and the peak factor. Comparing the given equation with the actual equation of the AC current, I equals Im sin omega t, we get Im equals 100 and omega equals 300. Thus, frequency equals omega upon 2 pi equals 47.74 Hz. The maximum value of the current is equal to Im equals 100 amperes. The RMS value of current is calculated as shown below. It comes out to be 70.71 amperes. Similarly, the average current is calculated as 0.637 into maximum value. The formula for the form factor is the ratio of RMS current to the average current, which comes out to be 1.11. The peak factor is given by maximum current upon the average current, that comes out to be 1.414. We have seen that the sinusoidal signal is plotted V versus omega t. Thus, y-axis represents the instantaneous magnitude and the x-axis represents the time instant t. The origin is considered as the reference position for plotting the signal. The AC signal is a continuous signal. It may or may not start from the origin. The difference between the reference position and the point where the signal attains the zero value first time is called as phase angle and represented by symbol phi. Thus, we have three possible cases as phase angle equals 0, phase angle is negative, or phase angle is positive. Let's see them one by one. In the case where phase angle is 0, the sine wave attains 0 value at the origin only. Thus, the difference between the 2 points is 0. In the second case, we have negative phase angle. When the sine wave attains the 0 value after the reference position, the phase angle being the difference between two positions becomes negative. In the last case, we get the positive phase angle as the signal attains the 0 value before the origin, and the difference between the two positions becomes positive. The phasor diagram is the vector representation of the signal. It is plotted with respect to x-axis, taking the magnitude and the phase angle. Thus, when phase angle equals 0, the phasor of the signal becomes parallel to the x-axis. When phase angle is negative, the phasor is drawn below x-axis at an angle equal to minus phi. And when the phase angle is positive, the phasor is drawn above x-axis at an angle plus phi. From this, we can conclude that if the direction of the rotation of phasor is anti-clockwise, the phase angle is positive, and if the phasor rotates in the clockwise direction, the phase angle is negative.
Hey, it's time to concentrate now.
Now let's plot the two alternating signal voltage and current having same frequency but different magnitudes. If both these signals attain 0 value at the same time instant, say t1, and the maximum value at the same time instant, say t4, then the two signals are said to be in phase with each other. Thus, their phasors also coincide with each other as shown. But if these two signals attain the 0 magnitude at different time instances or the maximum magnitude at different time instances, the signals are said to be out of phase with each other. To draw the phasors of such signals, one signal, generally the voltage, is considered as the reference signal and is drawn on the x-axis. The second signal is drawn either in the clockwise or in the anti-clockwise direction depending on the phase angle. The mathematical representation of any phasor is called as the Phasor algebra. This phasor can be represented in two different ways, such as rectangular form and polar form. In rectangular form, we represent the phasor in the form of a complex number as x plus iy, where x is the real part and y is the imaginary part. The magnitude is calculated as the square root of the real part square plus the imaginary part square, and the phase angle as tan inverse of the imaginary part upon the real part. In polar form, it is shown in the format magnitude and the angle. Again, the phasor angle is taken as positive if it is measured in an anti-clockwise direction, and it's negative if measured in the clockwise direction. AC current flows through the circuit when the AC voltage is applied to it. And it is not necessary that both the signals must be in phase always. Sometimes these signals are out of phase with each other. Depending on this, we divide the AC circuit into three main types as shown. Consider pure resistance R connected across the AC voltage source given by V equals Vm sin omega t. The current that flows through the circuit is given as I equals V upon R. Substituting the instantaneous voltage, I equals Vm sin omega t. If we consider only maximum values, then the maximum current is given as Im equals Vm upon R. Thus we get I equals Im sin omega t. Comparing the equations of the instantaneous voltage and the current, we see that both the signals are in phase. Thus, in purely resistive circuit, the voltage and the current are always in phase. As V and I are always in phase, the power consumed by resistance is always non-zero. Now consider that the pure inductor is connected instead of the pure resistor. The alternating current flowing through the circuit sets up the magnetic field around the inductor, and the EMF is induced in it. This EMF is called as self-induced EMF and is given as L into di by dt. At any time instant, self-induced EMF is equal and opposite to the voltage applied. Thus V equals L into di by dt. Writing the equation for current, we get I equals Vm upon L integration sin omega t dt. On solving the integration, we see that I equals Im sin omega t minus pi by 2. Thus the voltage and current are out of phase, with the current lagging behind the voltage by 90 degrees. Thus for a purely inductive circuit, the current lags behind voltage by 90 degrees. For the first half of 90 degrees, the voltage is positive and the current is negative. Hence power becomes negative and it flows from the inductor to the source. For the next 90 degrees half, the voltage and the current both are positive, leading to the generation of positive power from the source to the inductor. These two powers cancel each other and hence the power consumed by the inductor becomes zero. The inductance is given as XL equals 2 pi FL. Now let's consider the circuit with the capacitor only. As the AC current flows through the circuit, the capacitor develops the charge across its plates as Q equals C into V. The current is given as I equals dQ by dt. Substituting the value of Q, we reach the equation Im sin omega t plus pi by 2. Thus in this case, the current leads voltage by 90 degrees. Hence in a purely capacitive circuit, the current leads the voltage by 90 degrees. In purely capacitive circuit also, the power absorbed in the capacitor is zero. The capacitance is given as Xc equals 1 upon 2 pi Fc. Consider an example. 20 millihenry inductor has the current of I equals 7 cos 1000 t amperes. Obtain the voltage VL across it. And for the capacitor of 412 microfarads, find the capacitive reactance. The given equation is I equals 7 cos 1000 t, but the standard equation is I equals Im sin omega t. Thus we first convert the cos function into the sine function. Hence the equation for the current changes to I equals 7 sin 1000 t plus pi by 2. Thus we have Im equal to 7 amperes, omega equals 1000 and phase angle equal to pi by 2. The RMS value of current is obtained as I equals Im by root 2 equal to 4.949 amperes. The inductor reactance is calculated as XL equals 2 pi F into L, which comes out to be 20 ohms. Thus the voltage VL is calculated as the product of I into XL and comes out to be 98.98 volts. The capacitive reactance is calculated as Xc equal to 1 upon 2 pi Fc, which comes out to be equal to 7.72 ohms. Let's have a quick review of what we've learned in this lecture. The magnitude of the DC signal is constant, whereas the magnitude of the AC signal continuously changes. Because of the sinusoidal nature, the sine wave is represented as V equals Vm sin omega t. The different terminologies used in the analysis of the signal are instantaneous value, amplitude, time period, and frequency. In case of the AC circuits, the values of the voltage and the currents are expressed in three different ways, such as the peak value, average value, and the RMS value. If the sine wave attains zero value at the reference position only, the phase angle is said to be zero. If the sine wave attains zero value after the reference position, the phase angle becomes negative, and if it attains zero value before the reference, then the phase angle becomes positive. If the two signals attain their zero value and maximum value at the same time instance with respect to each other, the signals are said to be in phase, else they are out of phase with each other. The three types of AC circuits are considered as the fundamental circuits: resistive, inductive, and capacitive. For resistive circuit, the voltage and the current are in phase with each other. For the inductive circuit, the voltage leads the current, whereas in the capacitive circuit, the voltage lags the current.